This is a timing diagram for an MRI pulse sequence. These 5 simultaneous plots of time are essentially the sheet music for an MRI scanner, telling each instrument within the scanner exactly what to do and when in order to produce an image. The top plot shows transmitted RF pulses. Then we have a collection of magnetic field gradient plots in each of 3 orthogonal directions, showing the gradient magnitudes and durations. And then the bottom plot tells us when to switch the spectrometer on to detect and record any RF signals within the tissue. It's often called the ADC since it notes when analog to digital conversion is taking place. This particular timing diagram illustrates the gradient recalled echo, or just gradient echo, pulse sequence. And it is the foundational sequence in MRI. If you want to know how MRI pulse sequences work, you should really start with this one because every other pulse sequence builds off the concepts introduced here. That's the goal of this video, to get you to understand the gradient echo pulse sequence. First, a quick reminder of the basic principles of NMR which we've detailed in the previous lectures, links in the description below. In the presence of a magnetic field, nuclei possessing a magnetic moment will demonstrate precessional motion about this magnetic field. Collectively, the quadrillions of spins in space sum to a nuclear magnetization vector m, which is well described by the Bloch equation. This says that the rate at which a vector m changes in time is proportional to its cross product with the external magnetic field, b. The proportionality constant, gamma, is called the gyromagnetic ratio and can be either positive or negative. Solving the Bloch equation reveals that m will precess with angular frequency omega equal to its gyromagnetic ratio times the external magnetic field strength. So a stronger magnetic field results in faster precession and a lower field slower precession. This expression is called the Larmor equation, and it's all we need to produce images of tissue. Just FYI, the magnetic moment m is often referred to as a spin in imaging context, even though it's actually a collection of individual spin magnetic moments. Now, animation of the precessing spin here is shown in what we call the laboratory frame of reference, since this is what it looks like spins are doing outside of the system. But sometimes, it's much easier to think of aspects of image production in a frame of reference which rotates at the spin's resonance frequency in this magnetic field. This is called the rotating frame of reference, and I'll draw its perspective over here. Now when I increase the field strength, the spin precesses faster than our rotating frame's frequency, and we see a positive precession relative to the rotating frame axes, and negative precession if the field strength is reduced. So the rotating frame essentially illustrates the spin's frequency difference from Larmor resonance rather than the actual spin frequency. Notice how I animated the magnetic field vector in the rotating frame. In this frame, an effective magnetic field must be substituted for the true field strength if we want the Bloch equation to remain valid. The math of the rotating frame will be a topic for a future video. All I want to do here is get you to see the 2 ways I plan to animate spins in this video. Both of these visualizations will be handy to us in learning MRI. The laboratory frame is great for visualizing spin frequencies, and the rotating frame is nice for examining spin phases. As we've said in past lectures, we only detect the transverse component of our spin behavior, so to further simplify, I'm very often going to take a top-down view of spins. Of course, from this perspective, you can't really see the magnetic field very well, so I'll introduce a magnetic field color scale to help us out, and I'll color the spins themselves according to the magnetic field they experience. This sort of off-green color is Larmor resonance, higher fields are warmer colors and lower fields cooler colors. Notice that when looking down the magnetic field like we're doing here, clockwise precession notes increasing phase, so that's how I plan to animate it in subsequent slides. But it really doesn't matter. Gamma can be either positive or negative depending on the nuclear species. So coming up in the video, I'll have slides illustrating either magnetic field vectors or spin magnetic moment vectors, and I'll be sure to note which is which when they appear so we don't get confused. Now, the major concept to introduce here which makes imaging tissue possible is the magnetic field gradient. Consider a small collection of spins here, all at Larmor resonance in the laboratory frame. What we're going to do is alter the magnetic field B such that it increases linearly with space here. That is, the magnetic field increases as we increase our Y location. What will happen to our spins in this gradient? Well, since they're all in different magnetic field strengths, they all exhibit different frequencies. That's how we're going to localize spins in space and produce images. Different frequencies come from specific locations in space. But there's a problem, right? because we know the detected signal will actually be the composite sum of all spin frequencies. But you're not worried because you saw our last video on the Fourier transform. You know that if given any arbitrary signal f of t, the Fourier transform will deconstruct that signal into its individual sinusoidal components. Any individual sinusoid is mathematically described by a complex exponential of frequency omega, and each frequency omega in turn described by a single complex number called a phasor, which mathematically scales its sinusoid amplitude and shifts the sinusoid's phase. The Fourier transform is the operation which gives you the phasors big F of omega associated with every frequency omega, such that they are represented in the original measured signal. So the concept of the gradient echo is actually fairly simple. Imagine I have a collection of excited spin magnetic moments in space. I'll show both the laboratory and rotating frame representations. They're all processing in phase at their Larmor frequency in this magnetic field following excitation, and the detected signal from the sample will be the vector sum of all processing spins. So I'll show these vectors as well for each frame of reference. Now consider that I deliver the following magnetic field gradient in the x direction as a function of time. The gradient will be negative for a short time, then it will be positive for twice as long a time as indicated by the plot. Can you predict the behavior of our spins due to this gradient waveform? What about the detected RF signal from our spins? Well, down here I'll draw the detected signal plot. Laboratory frame signal in yellow, rotating frame in blue. Let's see what happens. When the negative gradient is delivered, the spins dephase and the signal sum is reduced as they lose coherence. But when the positive gradient is delivered, the spins eventually regain their coherence, resulting in a signal peak and subsequent continued dephasing following. The signal peak here is called a gradient echo, and that's pretty much it. Unlike the spin echo, which occurs due to the clever physics of refocusing pulses and T2 star decay, the gradient echo is entirely manufactured by the gradient. This may seem trivial or underwhelming, but what makes this so valuable is that we are directly controlling the frequencies and phases of spins based on where they are in space. This will be the key to localizing spins and producing images. So, how are we going to do it? Let's get a quick overview of the gradient echo sequence before we dive into the details. The gradient echo is typically divided into 3 separate steps: slice selection, phase encoding, and frequency encoding. The timing diagram shows only one repetition time for the sequence. See that the phase encoding gradient plot shows multiple paths? In order to reconstruct an image, we must repeat this full timing diagram multiple times, each time delivering a different phase encode gradient strength. Now, slice selection is highlighted here and involves exciting spins only within a well-defined 2D slice of the body. Once slice selection is performed, we know any detected signal came from this plane. Here I'm showing an axial or transverse slice, which is perpendicular to the superior-inferior axis of the body. Axial slices are displayed with anterior on top, posterior on the bottom, but note that the right side of the body is on the left side of the image and left on the right. It's like we're looking up through the patient's feet. This is standard radiological orientation, although neurologists often prefer to swap the right-left. Slice selection can excite spins in any 2D plane you like. Here's a coronal slice, again right side of the body on the left side of the image and vice versa. It's like the patient is facing you. And here's a sagittal slice. But you're not restricted to the 3 cardinal directions. Any slice orientation is possible in an MRI. Once we've excited spins in a desired slice, we perform phase encoding. I'll zoom in on our slice to show the individual voxels we want to resolve. Each voxel essentially contains its own spin magnetic moment vector, shown in the rotating frame here. The voxel brightnesses, in fact, correspond to the spin magnitudes and are dictated by the specific contrast mechanism chosen for the desired image, T1, T2, etc. So you can think of your patient as a big 3D collection of magnetic moment vectors, and the goal of the MRI pulse sequence is to somehow measure each voxel's magnetic moment. The phase encoding step involves delivery of a short gradient orthogonal to the slice selection axis, which increases or decreases spins precession phases according to their location along this dimension. Thus, it encodes the spin locations by phase. Finally, we perform frequency encoding. We deliver a third gradient orthogonal to both slice select and phase encode gradients. Spins in the higher field will precess faster than spins in the lower field according to the Larmor equation. Thus, this dimension is encoded by the respective spin frequencies. During frequency encoding, the ADC is switched on, as the plot indicates, and we record the incoming NMR signal. This is called the readout. And the terms frequency encoding and readout are often used interchangeably by MRI folks, which is why my frequency encode gradient is called G sub RO here. So there's the qualitative overview of the gradient echo sequence. I find that very often textbooks will stop here, leaving you with the pulse sequence procedure, but little understanding of why the protocol is set up this way and how each step works. My goal here is to elucidate the connection between the physics, technology, and math as best I can, but don't get discouraged if it doesn't make sense all at once. MRI is a complicated technology, and every individual piece of this system was somebody's PhD dissertation. I'll do my best though. In order to get our discussion started, I'd like to return to our simplified view of the MRI scanner introduced in the very first video. The MRI consists of three major components nested inside of each other as shown here. The main B0 magnet in purple, gradient coil shown here as a simple green cylinder, and RF coil in red. For this particular illustration, I've drawn the clinically common closed magnet design, so the scanner has the shape of a big tube. Now the magnet itself has exactly one overarching job within the system: create this and exactly this magnetic field. This says that the magnetic field be at every location XYZ within the scanner bore should be a vector of magnitude B0 and pointing in the positive Z direction. The arrows I'm drawing in my illustration here are the magnetic field vectors, not spin magnetic moment vectors just yet. Now the precision to which this equation must be satisfied is no small feat of engineering. The field must be perfectly collinear with the Z-axis, so no X or Y components, and the strength of the magnetic field cannot vary in space. As we saw in part 2, even a difference of 1 part per million in the field strength can reduce our T2 star to milliseconds, so microtesla differences matter here. Now, obviously, this is impossible to achieve for the whole field, so what we really mean is that the field must satisfy these conditions to a specified degree of precision within a specified volume of the scanner bore, called the imaging volume. Here's a figure showing a typical magnetic field strength within the imaging volume using a color scale to indicate field strength. Link to the source in the description. The very center of the magnet bore is called the isocenter, and is the location where these field conditions are best met. So we always try to center patients as best we can to this location. When loading a patient into the magnet, the technologist uses a laser sight built into the scanner to position the anatomic location we intend to image. And once marked, the scanner draws the bed into the bore such that the target tissue is as close as possible to isocenter. Now the field created by the B0 magnet is ideally completely static in time. In order to alter the field dynamically for imaging, we need this second layer of our MRI, the gradient coils, or gradients for short. While I drew the gradients as a big green cylinder in the cartoon, in reality this cylinder consists of 3 separate sets of conductive coils designed to create linear magnetic field gradients in X, Y, and Z directions within the imaging volume. Their job is to modify the field equation so it looks like this. Here we see that the gradients serve the purpose of altering the B field in X, Y, and Z by adjusting the values of Gx, Gy, and Gz respectively. If all the gradients are off, all G values are 0 and B is just B0 everywhere. By flowing current in the gradient coils, we create additional magnetic fields on the bore, which creates a spatially varying magnetic field strength. The G factors are the gradient strengths and are most often reported in units of millitesla per meter. Multiplying by our X, Y, and Z locations in meters gives the magnetic field at that location. And so for example, if G sub Z is 3 millitesla per meter, then the magnetic field increases by 3 millitesla for every meter we move in the positive Z direction. So to illustrate, here's an example of a positive gradient in Z. As our location in Z increases, so does the field strength. A negative gradient in Z would do the opposite. Here's a positive and negative gradient in Y, and a positive and negative gradient in X. Hopefully you notice that a gradient in X or Y does not mean the magnetic field vector itself has any X or Y component. It's the strength of B which must vary in space, not the direction. That's why the full magnetic field expression is all part of the Z hat component of B. So just like with the main B0 magnet, the gradients must create the linearly varying fields to a high level of precision. So how are these gradient coils actually constructed, you might ask? Well, gradient coil design is its own subdiscipline in MRI and far beyond the scope of our discussion today, but here's a 2-bit rundown just to give you an idea. For a Z gradient, consider a single loop of wire with a current running through it like this. According to the Biot-Savart law, this current path will create this axially symmetric magnetic field near the loop. Place another loop of current coaxial to the first one and send current around this loop in the opposite direction. Now we have this magnetic field. Zooming in and filling out the space with magnetic field vectors, we see there is a small volume where a linear magnetic field gradient in the Z direction is created. Field is increased at one end of the volume and decreased at the other. I'm drawing the actual magnetic field of this 2-loop cartoon, so it's far from perfect, but real-life Z gradients are designed with this principle in mind and create much more accurate gradients over a much larger imaging volume. And this 2 coaxial loop design is called a Maxwell pair. For the X and Y gradients, imagine that I could take the same wire loop but cut it in half horizontally. Then I'll send current in these directions for the top and bottom halves respectively, and that current flow will create this magnetic field. Check it out, right in the middle is a linearly varying field in Y. Field increased in the Z direction at the positive Y and decreased at the negative Y. Again, it's not perfect here due to the simplicity of the 2 half-loop design I'm modeling, but real-life gradients build off this design known as a saddle coil or Golay coil design. The X gradient is exactly the same as the Y, by the way. Just copy, rotate 90 degrees, and paste. So that's a very introductory introduction to gradient design. Nowadays, gradient experts employ sophisticated field simulations, finite element analyses, and even AI in gradient coil design. Finally, the innermost component in the MRI is the radio frequency or RF coil, which transmits RF to spins and receives RF from spins, though not at the same time. The coil here is built into the magnet bore and is called a birdcage design. It looks like a ladder wrapped around a cylinder. And actually, while it can perform both transmit and receive tasks, reception of signal from tissues is often done with separate coils placed closer to the anatomy of interest. Birdcage coils like this are designed to deliver very spatially homogeneous RF excitation pulses to all spins within the volume, so all spins experience the same flip angle. In the context of MRI, the magnetic field component of the RF is called the B1 field, distinct from the main B0 field. The specifics on design of MRI coils is going to have to wait for a different day, but for now, I just want you to keep a few rules in mind regarding MRI coils. Rule 1. The coil is in no way spatially selective in delivery of RF. For instance, you might think that if we wanted to image the heart, that somehow the coil directs the RF only to spins within the heart. But that's just not how it works. Everything inside the magnet bore experiences the delivered RF. But Rule 2 says that only spins whose Larmor frequency matches the B1 field frequency will experience excitation. So in essence, Rule 1 says that all spins experience the RF, but Rule 2 says not all spins experience excitation. So if we were to create a magnetic field which varies in space, i.e. a gradient, we can alter the spin's Larmor resonances in space and thus only excite spins in the desired locations in the sample. That's the idea behind slice selection, exciting only a specific volume of spins in the body for subsequent detection. Finally, Rule 3 of the RF coil has to do with detection of the NMR signal. The coil detects the vector sum of all the spins with transverse magnetization. So let's see how all this works. For our discussion today, I'm going to image 2 jars of water here called phantoms. Phantoms are just prepared samples with known geometries, T1s, T2s, etc., that you image for the purpose of sequence testing, quality control, or calibration, essentially non-living patient things. And we'll image the water tubes with axial slices today. That means our excitation slice will be perpendicular to the z-axis like this. I'm choosing this phantom because it's a simple geometry but with some defined structures, so we'll know exactly what to expect once our MRI is reconstructed. Okay, so let's zoom in on the spins in our phantoms and see what's going on. Here's our spins in the phantom in equilibrium, all pointing in the direction of the B0 field. I'll draw the slice we want to excite around these spins here, and I'll place our magnetic field color scale here. Remember, these arrows are not the magnetic field vectors, they are the spin magnetic moment vectors, which I'm going to color according to the magnetic field strength they experience. Right now, they're all experiencing the same B0 field strength. Now how do I excite only spins within our desired slice? Yeah, well, we'll employ Rule 2 here. Only spins whose Larmor frequencies match the B1 field frequency will experience excitation. So imagine we turn on a gradient in the z direction. Now, the magnetic field B is not a constant in space, it is equal to the gradient strength G times position in the z direction. And thus, each spin's frequency is gamma g sub z times z. Now the slice we wish to excite spans a defined distance. For example, if we want a 2 mm thick slice at isocenter, then the left and right edges of the slice are at -1 and +1 mm respectively. By applying a gradient, we assign a magnetic field strength to these locations in space. For example, if we apply a gradient strength of 50 millitesla per meter, then the left edge of the slice is at field strength 2.99995 Tesla, and the right edge at 3.00005 Tesla. In turn, the gyromagnetic ratio of the spins assigns precession frequencies omega to each magnetic field strength. So for protons of gyromagnetic ratio 42.577479 MHz per Tesla, the left and right edges of our slices are at these respective frequencies. So, we know that the 2 mm slice thickness corresponds to this band of frequencies delta omega equal to 42.578 kHz in this example. This is called the transmit bandwidth. Bottom line, the gradient connects physical locations in Z to specific frequencies omega. So by delivering a B1 pulse, which contains all the frequencies in the band, we excite all the spins in the slice and none outside of the slice. So I'll make a plot of the B1 field strength we want to deliver as a function of frequency, which is 0 everywhere except in our slice. So what B1 pulse as a function of time contains all the frequencies within this box? Well, it will contain this frequency here, and this frequency, and all the frequency spanned by the continuous frequency band delta omega. Would you look at that, it's a sync pulse, sine of stuff over stuff. Yeah, but of course you're not surprised because you saw our last video on Fourier transforms where we showed that the Fourier transform of the sync function is the square pulse and vice versa. The transmit bandwidth is inversely proportional to the sync pulse lobe duration as we've seen before, and slice thickness is directly proportional to transmit bandwidth by the Larmor equation. Slice thickness can also be altered by the gradient strength. If I make a plot of frequency versus position, the slope of this yellow line represents the gradient strength, G, and a specific center frequency and bandwidth maps to a slice location and thickness. So we can change the slice thickness by modifying the bandwidth, or by changing the gradient strength. Nearly every MRI textbook has some version of this plot making that connection. Okay, so let's return to our spins, and I'll draw the timing diagram here with our excitation pulse and slice selection gradient. Since we're looking at an axial slice, for our illustration today, the Z gradient is our slice select gradient, and I'll use Y as the phase encode gradient and X as frequency encode in our example today. So let's play our sequence and see what happens. Neat! Spins at the exact location we wanted with the precise slice thickness we wanted have been knocked into the transverse plane of the magnetic field. Except, do you see any problems here? Yeah, they're all out of phase with each other, all pointing in different directions. Remember, Rule 3 says that the signal we detect is the vector sum of all the excited spins. So this is a problem, because now their vector sum is nearly 0. How did that happen? Well, notice that during the application of the gradient, spins in the higher field will have a higher Larmor frequency and low field a lower frequency, so during the process of excitation our spins are dephasing across the thickness of the slice. So any ideas on how we can fix this? Yeah, sure, just play the gradient backwards and the spins will rephase. Now their vector sum is a detectable magnetic moment. In our timing diagram, we've added a rephase lobe to the slice select gradient, which is half the total area of the excitation gradient lobe. So if the slice selection gradient has area A, the rephasing gradient has area A over 2. This is because you can actually model the system pretty accurately as if all the spins experience instantaneous excitation at the peak of the sync pulse. Thus the accumulated dephasing occurs only for the second half of the excitation gradient. So now we know that a desired slice thickness combined with an applied gradient strength dictates a specific transmit bandwidth, which in turn dictates a particular B1 magnetic field function of time, the sync pulse. But that's only half the story, right? How exactly do we control the location of the selected slice? Well, there's an important detail that's been absent in our discussion so far, and that is that the sync pulse here is not the B1 pulse delivered to the spins, rather it is the envelope which modulates a carrier frequency tuned to the spin Larmor frequency at the center of the desired slice. If the slice is centered at a location Z0, the Larmor equation dictates a specific frequency omega0, which is the carrier frequency modulated by our sync function. So why does this work? Well, remember that multiplying a function by e to the I omega naught t has the effect of shifting its Fourier transform over by omega naught. This is called the Fourier shift theorem, which you remember from our last adventure. So higher or lower carrier frequencies effectively shift our slice location to locations within the gradient of higher or lower magnetic field. And that, my friends, is slice selection. Our spin sample is a 3D distribution of magnetization vectors, but following slice selection, we know that any signal your system detects came from within this location Z0 within the magnet. Thus, slice selection has reduced the problem from 3D to 2D, which in this example is just a cross-section of the two tubes. As we walk through the math in the next steps, keep your eye on this m sub xy, as this is the 2D map of spin magnetization. It's the image we're trying to find. The gradient echo is what we call a 2D multi-slice MRI scan. Each 2D image we construct from a single slice has its own 2D K-space to be filled and Fourier transformed. Now let's actually examine the 2D map of magnetic moments in our slice. Here's a collection of spins immediately following excitation and slice refocusing. Now we know the transverse component of a magnetic moment dictates the signal it delivers, so each spin at a given xy location is delivering its own signal S, which in the rotating frame is just its complex phasor, local magnetization vector m sub xy, times its corresponding phase vector e to the I phi, where both m and phi are location specific in x and y. But we don't detect just one spin. Rule 3, again, says we detect the vector sum of all spins in the sample. So mathematically, our detected signal S of t is the integral of all spin magnetic moments across x and y. So this expression actually describes what the coil sees. And somehow we have to reconstruct our image m sub xy from our recorded signal S sub t. Does this expression look familiar? Sure looks like an inverse Fourier transform, right? But not quite. Can you see what's missing? We're integrating over space here, dx and dy. The only way this is a Fourier transform is if variables x and or y exist in linear form somewhere in the exponent phi. So, what is phi of an individual spin at some location xy? If we're perfectly at Larmor resonance, the spin is perfectly stationary in the rotating frame here. But in a higher field, the spin will accumulate phase and in a lower field lose phase. Remember that the rate at which phase phi changes in time is, by definition, omega, its angular frequency. So if we know omega, we know phi just by integrating with respect to time. Omega is of course the Larmor frequency, equal to gamma b. And in the presence of magnetic field gradients, b is equal to g sub x times x plus g sub y times y, where g sub x and g sub y can be functions of time. Thus, this is our phase phi. The magic here is that we control the gradients gx and gy, and thus we control phi, and e to the I phi becomes a known in the signal equation. So, we measure s, we know phi, and we solve for m. Does s look like a Fourier transform now? Yes, it is. Phi is a linear function of x and y, and so our signal S is indeed a Fourier transform of m sub xy. Now, I want to visualize exactly what the gradients are doing to our spin map. How about we start by applying a gradient in the x direction? Our magnetic field is now equal to the gradient strength gx times x. What will happen to our spins? Well, let's see. In this laboratory frame animation, spins toward the right experience a higher field and thus exhibit a higher precession frequency, and those toward the left a lower precession frequency. And all frequencies in between are delivered in accordance with the spin density at a given x location. Notice that certain frequencies, like this one, have higher amplitudes because there are more spins in the center of the phantom's circular profile, and likewise, fewer spins exist in the edges of the circle, yielding a lower amplitude frequency. But, again, Rule 3 says the coil detects all spin signals simultaneously to yield S of t. So what is phi in this scenario? Let's bring our spin phase equation back and see. There's no y gradient, so that term drops out, and the x gradient g sub x is just a constant, so our phase just simplifies to this. Plug into our signal equation and we have this expression for a detected signal. If I rearrange the expression a bit, you can see more clearly that the blue portion of the equation is the integral of m with respect to y and is so just a sum of spin magnitudes in the y direction. In other words, our signal is the inverse Fourier transform of a 1D projection of m sub xy onto the x-axis. So the 1D Fourier transform of S of t will give us back the individual sinusoid amplitudes as a function of frequency, our 1D projection of m in the direction of the applied gradient. Look at that! You can see the projected profile of the two water phantoms on the omega axis, which, thanks to the gradient, translates to the x-axis. This is called frequency encoding, since the spin frequencies tell us which x locations they came from. So from our 2D map of spins m sub xy, we have constructed a 1D projection of m. Any ideas on how you might get the second dimension back? You might think it's as easy as doing the same thing but with a y gradient, but this would only give us another 1D projection just in the y direction, not the 2D map of spins we want. And any combination of x and y gradient strength simply yields a different projection angle through the sample, but we still only have a 1D projection. But wait, you say. What if I did this? Apply a gradient, record the signal, and Fourier transform to get the projection profile at multiple gradient angles for each acquisition. Here on the right, I'm showing an image of all these projections, letting each row of pixels be a single projection at a specified angle. This is called a sinogram. Then, to reconstruct the image, I'll just take each projection we collected and kind of smear it back across the image space at the angle it was collected. Adding up all the smeared projections in this way will yield a reconstruction of our image. If you're thinking along those lines, then you have the exact idea Paul Lauterbur did when he published the very first MRI in 1973. This technique is called back projection, and it's pretty much the exact idea behind how a CT scanner reconstructs images. Maybe we can do a video on how CT scanners work sometime if you'd like. Turns out, though, that the math of MRI affords us a much more elegant method of image acquisition and reconstruction. Let's get back to this slide of our spin map and Fourier projection. I'm going to return to the rotating frame here to make it easier to visualize the next step, so spins at Larmor resonance will appear stationary, no precession. Did you notice my sleight of hand on this slide earlier? The projection profile I'm drawing down here is not the Fourier transform of our acquired signal S of t, it is the magnitude, or modulus, of the Fourier transform, which is in fact complex. This function contains both real and imaginary components, which I'm now showing in green and purple respectively. Each location along the omega axis of our Fourier projection contains a complex phasor, which itself is the vector sum of the spin phasors located at that corresponding x location in n sub xy. Immediately following excitation, all the spins have the same phase and thus point in the same direction, along the positive x or real axis. So the Fourier phasors at each omega location in our projection are just real numbers whose magnitude effectively tells us the number of spins at this x location, but not their y locations. However, consider that just before we perform frequency encoding, I play a gradient in the y direction, but just for a short amount of time. What will happen to our spin map? Well, the spins in the top right phantom are above the y-axis isocenter, and so will experience an increase in field strength and will all gain phase during the gradient. Conversely, the spins in the bottom left will experience a reduction in field strength and lose phase. So consider this column of spins from the top phantom. They all sum to the phasor corresponding to this location on our Fourier plot. So this collection of spins sums to this Fourier phasor at that omega/x location. I'll also do the same for a column of spins in the lower phantom experiencing the reduced field, and their summed phasor. Now let's watch what happens when we deliver the Y gradient for a short amount of time. The spins in the top phantom increased in phase, leading to a new phasor sum which is now along the negative imaginary axis. The spins in the bottom phantom did the opposite. The acquired signal has thus changed slightly, and the Fourier projection shows reduced phase on the left and increased phase on the right, reflecting the different positions of the spins in each phantom. So here's the take-home: by winding up spins perpendicular to the frequency encoding direction, the phase change we induce reflects the overall spin locations in the perpendicular dimension. This step is called phase encoding. Now, it probably doesn't make perfect sense just yet, but let's continue with the math just like we did with frequency encoding and see what we learn. This time, we play a constant Y gradient for a short time tau, and then a constant X gradient during signal acquisition. So our phase expression becomes this, and plugging into our signal equation yields this. Integral over all space of m sub xy times the phase encode kernel, and a frequency encode kernel. And that, my friends, is an explicit 2D Fourier transform. The signal collected during application of gradients are in fact complex phasors corresponding to specific 2D spatial frequencies. So knowing that, what are the gradient waveforms in X and Y we need to precisely craft our acquired signals such that we can reconstruct an image? Enter the K-space formalism. Let's quickly remind ourselves of the math and magic of discrete K-space, which we learned from the last video, again link in description. Similar to 1D functions, 2D functions such as images can be represented as a sum of sinusoid waves. For 2D functions, these sinusoids are also 2D and look like these stripe patterns. We can organize these sinusoid patterns according to the number of wavelengths which span their X and Y dimensions, the spatial frequencies Kx and Ky respectively, on a 2D grid like I've done here. Thanks to the math of complex exponential functions, we can simplify this diagram by noting each 2D sinusoid's amplitude and phase with a complex phasor like this. The image on the left is a function of space, xy, whereas the corresponding grid of phasors on the right is a function of spatial frequencies, kx and ky. This complex phasor function is the 2D Fourier transform of the image, so each location in K-space represents a particular 2D sinusoid, and the phasor stored at that location dictates the amplitude and phase of the sinusoid as it contributes to the image. The relationship between a discrete image and discrete K-space can be summarized by their own set of 3 rules. 1. The spacing between discrete K-space frequencies is inversely proportional to the image fields of view in X and Y, leading to a K-space grid separated by discrete steps of delta Kx and delta Ky. Note that X and Y fields of view are not necessarily equal, and thus the step sizes in K-space are not necessarily equal. Rule 2. The desired voxel size in the image dictates the locations of the Nyquist borders in K-space. Given a discrete spacing between pixels, the highest spatial frequency which can be accurately reproduced can have a wavelength no shorter than 2 pixels. Note that the pixel dimensions delta x and delta y are not necessarily equal, and thus the Nyquist border locations in Kx and Ky are not necessarily equal, although in MRI, isotropic pixels are generally always preferred. Finally, the 2 grids of data will have the exact same number of data points in x/kx and y/ky. And note that if you have any 2 of these rules, the third follows. Okay, let's get back to our spins and see if we can figure out how gradients in K-space are connected. Consider a 2D slice of excited spins in the rotating frame as I'm showing here. I'm going to deliver the following gradients shown in the top right to these spins. First, a positive gradient in the y direction shown in the green plot, and then a positive gradient in the x direction shown in the red plot. As we deliver the y gradient, spins accumulate phase in the rotating frame linearly according to their location in y. Do you see it? Let's continue with a gradient in the x direction. Same deal here, spins acquire phase linearly in x. Do you see it now? By winding up spins in space using these linear field gradients, we're creating our own spatial frequency within the sample. This 2D sinusoid we've created here corresponds to a particular location in K-space dictated by the number of wavelengths per unit space in the x and y dimensions. This spatial frequency right here has two wavelengths across our field of view in x and also two wavelengths across y, so we know this corresponds to the location kx equal to, ky equal to in discrete k-space. So applying gradients to our excited spins walks us around in k-space. Oh, and note that there's no ambiguity here in the direction of phase progression. We know we're at kx, ky equal positive 2 and not negative 2 because phase increases as we move across fringes in the positive x and y directions. So now let's see if we can find an expression which tells us our exact k-space location given a particular gradient. This is our expression for the phase of a spin at location x and y given gradient functions of time gx and gy. Now spatial frequency k is, as its name suggests, a number of cycles or radians per unit distance in space. That is, it is the change in phase per change in distance. This should seem familiar as we know a temporal frequency omega is change in phase per unit time. Anyways, in two dimensions, this would give spatial frequencies in both x and y, kx equal to d phi dx and ky equal to d phi dy. Taking these derivatives of phi leads us to these expressions for spatial frequencies kx, ky. Or, in general, a spatial frequency k equals gamma times the integral of a gradient waveform in time. And that's our mathematical connection between gradients and k-space. So from this, we see that our phase at any given location simplifies to kx times x plus ky times y. That means our detected signal as a function of time is in turn a function of kx and ky, our 2D Fourier transform directly connected to our gradients. So, going back to our gradient plots, can you figure out what our k-plots would look like? Yeah, sure, they're just the integrals of the gradient plots in time. The area under a gradient curve in time tells us our k value and thus our location in k-space. So given our example gradients from earlier, this is our kx and ky as functions of time. These parametric kx, ky plots in turn provide a well-defined trajectory in k-space. Can you see what that trajectory is? We always start at the k-space origin or DC offset immediately following excitation. Then the kx, ky plots show first an increase in ky, then an increase in kx, giving this path through k-space. I'll play that out as an animation here, and I'll add brightness maps of the real and imaginary parts of our spin map as well. See how the gradient waveforms are essentially plots of our velocities in kx and ky? They tell us how fast to move in either direction. The stronger the gradient, the faster we move around in k-space. Different gradient waveforms therefore define different trajectories through k-space. Check out the gradients in this example here. What would the kx, ky plots look like? What would our trajectory through k-space look like? Pause the video and see if you can figure it out before I spoil the solution. Well, we start with a positive x gradient and negative y gradient. Thus we're increasing in kx and decreasing in ky. In k-space, this looks like this. Next we have a positive gx and positive gy, so both kx and ky are increasing like this. We then switch to negative gx and positive gy, so we're decreasing in kx, increasing in ky. You get the idea. And here's the animation of the plots and their trajectory. How about these gradients? Can you see where we're going in k-space here? This is a spiral trajectory. It can collect the entire center of k-space in a single shot, which is great for rapid imaging of gross anatomy, though it requires relatively long readout times and is definitely more involved to code and reconstruct. There's all kinds of different ways to walk around k-space, each with their own advantages and disadvantages related to image contrast and quality. And now that we know exactly how gradients move us around in k-space, the final question to ask is, what is the signal our spectrometer collects? That is, what data or phasors should be stored at each k-space location along our trajectory? It all comes back to RF Coil Rule 3, the signal we detect is the vector sum of all spin phasors in the sample, and in its general form is written like this. Again, m sub xy is the unknown we're looking for, our spin map. Now that we have the gradient k-space concept down, I'll bring back our phantom image from earlier to be emps of xy. Here we're assuming the spins are all perfectly aligned with the positive real axis following slice selection. Phi and the exponent is something we completely control with gradients, which direct the kx and ky terms. So the complex kernel is a vector map which looks like this. Multiply the two together and you have the exact spin map we're trying to find the vector sum of. With this representation of phase, our signal is an explicit function of kx and ky. As a really quick side note though, we're keeping our discussion simple today by assuming that all spins are excited into the transverse plane perfectly along the exoreal axis of the rotating frame. So emps of xy is entirely real and can be represented as a simple brightness map. But note that in general, emps of xy is complex. Excitation may not perfectly excite spins all with the exact same phase like we're showing here. Possible reasons for imperfect excitation can include B0 or B1 in homogeneity, motion of spins during the experiment, chemical shift or off-resonance effects, and a whole host of other things. If you're clever, you can design your pulse sequence to tease these dependencies apart and produce images which reflect the effects, such as fluid flow or physiologic activity. And yes, I do want to make videos about all of those at some point, but that's going to have to wait till later. Okay. So let's put all these pieces together and watch our signal come in as we encode spins. Here I'll put our spin map, emps of xy times our phase kernel in the rotating frame. Down here, I'll draw the stack of spins in our slice and also the vector sum of the spin stack. I'm of course scaling it down here so the vector sum isn't off the screen. These are just two visual representations of our detected signal, which is the k-space phasor. The stack before integration, the phasor after. Now right here I'll draw k-space, and as we play our gradients and move around in k-space, I'll draw our detected signal, a complex phasor, at its corresponding location. Let's use the two gradients we saw before, a y gradient then an x gradient. And I'll draw the real and imaginary kernels as brightness maps down here, which I think makes it a bit easier to see where we are in k-space. Alright, ready? Let's play the animation for the y gradient first. Okay, a lot just happened here and you may want to replay it a few times to watch everything. First, look at the spin map in the top left. After the y gradient, we've imparted a spatial frequency of 1 cycle per field of view. Spins at the top versus bottom of the image are 2 pi radians or 1 full cycle different in phase. Thus in k-space, we have moved up to ky equal 1. The spin stack at the bottom left shows the expected dephasing of spins following the gradient, and their vector sum, the phasor, is much smaller. So this spatial frequency, kx equals 0, ky equal 1, doesn't contribute much to the reconstructed image. Okay, now let's continue and play the x gradient. Look at this. We've wound spins up to a spatial frequency kx equal 1, ky equal 1 in k-space. And here, the spin stack demonstrates a clearer magnitude and direction, which is also reflected in the k-space phasor. So this spatial frequency, kx equal 1, ky equal 1, contains more information related to the overall spatial structure of our spin map. Alright, let's figure out how we want to acquire our k-space data and design a pulse sequence to do it. With the slice we've selected, we want to reconstruct an image with defined fields of view in x and y. This dictates the step size in k-space. We also prescribe a certain voxel size or resolution, which defines our k-space Nyquist borders. Our goal is to collect all these data points in k-space. Simple enough, right? So how would you do it? What gradient should we play to accomplish this? So as we've seen, there's lots of ways to do this, but the design of the gradient recalled echo sequence in particular is to collect one line of k-space at a time. Each line is one frequency encoded readout, and the lines are separated in the phase encode direction. So let's bring back our timing diagram and fill in the last few steps. Let's consider collecting just one line to start, say the very top line of k-space. Remember, following slice selection and refocusing, we're at the DC offset in the very center of k-space. So this k-space trajectory would look like this. What then should our encoding gradients look like? Well, we need a positive gradient in y simultaneous with a negative gradient in x to get us to the positive ky Nyquist and negative kx Nyquist. Then, a positive gradient in x will bring us across the kx dimension until we're at the positive kx Nyquist. While this gradient is playing, we'll switch on the ADC to collect the data. And there we have one repetition time, or TR. We'll repeat this sequence once for every line of k-space we need to acquire, each time with a different y gradient. On our timing diagram, we'll just draw multiple paths on the phase encode gradient to indicate this. That, my dear friends, is the gradient echo, or GRE, pulse sequence. We can also show the full pulse sequence with each TR explicitly drawn out. The TR is the time between excitations, and the TE is the time from the center of excitation to the center of the echo. And here you can see each individual phase encoding step leading to different acquired echoes, which fill different lines of k-space. And now let's get back to our animation slide and play the gradient echo. I'm only showing each TR's encoding steps here, understanding that the same slice selection is being performed for each TR. Isn't this fun? So we see that the gradient echo is essentially just a raster scan of k-space, one line acquired for each TR. Thus, if we need n phase encodes to fill k-space, then the time to acquire one image slice will be n times TR. Note that the frequency encode gradient time, or readout length, does not affect the scan time. Now, in the process of animating this slide, I populate k-space with the actual calculated vector sum of my spin map. So if everything I've said is true, we should expect that if I inverse Fourier transform this k-space data, I should get back my image. Well, I went ahead and did that, and look, a reconstructed image of our two phantoms. It's of course as equally low resolution as our k-space simulation, but I thought that was pretty cool, and an important verification that I coded my animations correctly. So there you have it, friends, that is the gradient echo MRI pulse sequence. Or well, at least, that's the bare bones explanation. There's some details you might want to note though. My diagram here shows block representations of gradients, but of course no gradient instantaneously ramps to its operating strength. There is a maximum rate at which a gradient can ramp up called the slew rate, often in units of millitesla per meter per second or something similar. The existence of the slew rate doesn't change any of our physics, but of course to accurately follow your k-space trajectories, your integrals will need to include those. The amplitudes of the gradients for phase encoding and frequency encoding follow the K formula. All you need to do is figure out what area under each curve is necessary to get you to your target spatial frequency. Now, based on our discussion today, you might be thinking, oh hey, phase encoding and frequency encoding are the exact same thing. They both just move us around in k-space. Why do we think of them separately as phase versus frequency? Does it even matter which k-space axis is which? The answer is, yes it does matter, because the data is digitized during the readout in the frequency encode direction, not the phase encode direction. So consider the following scenarios. Here I acquire my data during a relatively mild frequency encode gradient, so we just casually take our time filling in the k-space phasors here. On the other hand, what if I play a very aggressive frequency encode gradient and walk from edge to edge as fast as possible? If you believe the math, then we expect the same signal to be acquired either way. Can you see advantages or disadvantages to either of these? Well, one advantage to the fast readout is that the spins won't have dephased as much by T2 star decay compared to a long readout, so our signal will actually be a little bit higher in this scenario because our TE is shorter. On the other hand, a longer readout means we acquire data with a longer separation time between individual data point acquisitions, called the dwell time delta tau. The inverse of the dwell time defines the receiver bandwidth, not to be confused with the transmit bandwidth, which is completely unrelated. The receiver bandwidth defines operation of the spectrometer and has a few important consequences. One is that the signal-to-noise ratio of your image is inversely proportional to the square root of the receiver bandwidth. If you take 4 times as long to collect the same number of data points, you'll double your SNR, not counting T2 star decay. Another consequence is the fact that a temporal Nyquist frequency exists in the readout, which the phase encode does not have. Consider our sample with the yellow border defining our image. If we shrink our phase encode field of view, our K-space step size changes. Now when we phase encode, the scanner ensures that an integer multiple of cycles per field of view is reached. But look what happens to our spins outside the field of view. They all have phases which make them look like they came from the opposite edge of the image. And the reconstructed image will show what we call phase wrap artifacts. But what about in the readout direction? Well, because the readout is a real-time digitization, the spectrometer can filter out unwanted frequencies either using analog or electronic filters, or more commonly by oversampling the readout. We'll leave those details for another day, but the bottom line is it matters what direction you phase encode. Always try to ensure no spins are outside of the phase encode field of view. Okay, before we go, I have one last bonus sequence animation to show you. Check out the gradient waveform on the top right. Can you map the trajectory and K-space from these gradients? Pause the video here if you'd like to ponder before my animation spoils it. So let's watch it go. Here you see us collecting the entirety of K-space in a single shot by rastering each line back and forth. Now we collected all of our data in one TR. That's quite the speed boost. This multi-line acquisition is called Planar imaging and is very commonly used for speedy acquisitions. So if you followed along since the beginning and really want to test your MRI knowledge, here's a fun exercise you can work on. Share your solutions in the comments if you'd like. Perhaps we'll solve it together in a future video. And now that we've gone through some of the basics of MRI physics, we're finally ready to talk about the good stuff. Different pulse sequences like inversion recovery, stimulated echoes, diffusion tensor imaging, phase contrast, spin labeling, Dixon's method, fMRI, methods of acceleration, sense, parallel imaging, compressed sensing, hardware, how to make RF coils, gradients, magnets, spectrometers, image analysis techniques, chemical shift, hyperpolarized gases and contrast agents, MRI safety. Maybe you'd like to see other modalities discussed, X-ray, CT, ultrasound, nuclear medicine, and how they compare to MRI. Let me know, and we'll see you next time. Cheers, friends!